Watch the cockpit of this fighter jet as it executes a high-angle post-stall maneuver mid-air. It is completely empty. Public relations campaigns consistently frame the automation of the cockpit as a pursuit of absolute safety, a technological cure for human error. But beneath that narrative, the aviation industry is preparing to transition heavy kinetic infrastructure, multi-ton platforms carrying cargo and passengers at high velocities, over to non-deterministic software layers. This transition is a direct response to intense macroeconomic pressures. Major airlines and regional cargo networks are currently struggling against escalating labor expenditures and a severe chronic shortage of qualified pilots. Relieving that economic pressure by removing the human from the flight deck forces a complete restructuring of the aviation industry. It breaks a century of established aerospace software certification, exposes unencrypted flight buses to novel cyber-physical threats, and evaporates the existing legal frameworks for liability in the event of a crash. Airlines operate on razor-thin capital margins that are highly sensitive to labor costs. To satisfy strict flight and duty time limitations and maintain scheduling redundancies, European low-cost carriers must maintain a costly ratio of approximately 10 to 11 type-rated pilots per single airframe. To counter these margin-eroding forces, major aircraft manufacturers have aggressively lobbied regulators, like the European Union Aviation Safety Agency, to approve Extended Minimum Crew Operations, or eMCO. This table details exactly how these operational models compare. It measures a conventional two-pilot flight deck against the proposed eMCO standard and ultimately a fully uncrewed autonomous cargo fleet. The financial incentive is explicit. Extended minimum crew operations aim to reduce flight deck staffing to a single operator during the cruise phase, cutting crew overhead by up to 40%. To certify software where a failure would result in the loss of the aircraft, developers must provide objective evidence of 100% modified condition decision coverage. Every logical pathway must be directly traceable from the source code to the executable object code. Deep learning architectures, like convolutional neural networks, break this requirement entirely. A CNN does not operate on human-defined rules. It uses millions of statistical weights adjusted during training. Because requirements cannot be directly traced to specific lines of code, the decision-making process functions as an unauditable black box. To bypass this hurdle, regulators are attempting to establish new frameworks based on the concepts of design assurance for neural networks, or CODAN. This abandons classical verification in favor of a three-stage W-shaped development pipeline, emphasizing rigorous dataset curation and model architecture validation. During model verification, online, in-flight learning is strictly prohibited. The model is trained exclusively in a laboratory. Once error rates are acceptable, the neural network's weights are permanently frozen and treated as parameter data items. This forces the system to behave deterministically at runtime. Engineers then use statistical learning theory to quantify the risk. This equation mathematically bounds the generalization error of the frozen model within a defined operational domain, utilizing the Vapnik-Chervon-Kunix dimension to calculate structural risk. Despite these strict mathematical bounds, the statistical uncertainty inherent in neural networks remains far too high for regulators to trust them as a standalone primary flight controller. Because the AI layer cannot be fully trusted, developers are forced to implement a dual architecture paradigm. Hardware engineering steps in to physically govern the mathematical uncertainty of the software. Relying on strict ARINC 653 partitioning standards, specialized AI hardware accelerators are physically and logically separated from the primary, safety-critical, real-time operating system running on the aircraft's avionics cabinets. This schematic shows how the safety mechanism operates. If the non-deterministic AI controller hallucinates and commands an input that violates predefined flight envelope limits, like an excessive pitch rate, the deterministic DO-178C compliant legacy system acts as an external governor, instantly blocking the command and taking control. Commercial autonomous flight is currently viable only because rigid, legacy deterministic code is placed as a constant physical leash on the artificial intelligence. Plugging neural networks directly into primary data buses transforms the modern aircraft into a flying edge compute node. This tight integration exposes the entire flight control system to a severe vulnerability: adversarial machine learning. Adversarial machine learning does not rely on exploiting traditional programming bugs. Instead, it exploits the mathematical foundation of the model itself. An attacker can introduce subtle, human-imperceptible perturbations to sensor inputs, such as projecting specific laser patterns onto a runway, causing the vision-based landing system to hallucinate and deviate from the centerline. This is highly exploitable due to the insecure design of aviation communication networks. The primary commercial avionics bus, ARINC 429, and external ADS-B telemetry both operate without any native encryption or cryptographic authentication. This flowchart illustrates the attack vector. Any device that gains electrical access to the bus can inject spoofed rogue telemetry. Because the protocol lacks authentication, this temporal perturbation flows directly into the neural network flight controller, commanding the actuators without triggering latency alarms. The risk extends to the software supply chain. If an adversary gains access to the AI's training data, they can execute a data poisoning attack. By subtly mislabeling samples, they insert a dormant Trojan backdoor into the model before the aircraft is even built. The model will pass standard testing flawlessly, but when it encounters a specific trigger in the field, like a unique visual pattern or radio sequence, the AI will blindly process the spoofed or poisoned data as mathematically legitimate, executing an immediate, unprompted attitude shift. Integrating statistical models into commercial airspace completely dissolves traditional liability frameworks. Aviation law relies on a clear chain of accountability, flowing downward from the certified human pilot in command to the operating airline and finally to the original equipment manufacturer. Deep learning breaks that chain. When an autonomous aircraft misinterprets novel, out-of-distribution edge cases, like severe weather phenomena or heavy sensor noise, the resulting failure cannot be attributed to human operational negligence. As this chart maps out, assigning fault becomes highly complex. Blame immediately diffuses across a network of contributors. The airline argues the system was properly certified. The software developer blames gaps in third-party training data, and the original equipment manufacturer points to environmental sensor noise. Forensic investigators are unequipped to resolve this. Traditional flight data recorders are designed to log physical inputs, like control column deflections and engine parameters. They cannot record the millions of high-dimensional internal state activations of a neural network during the exact moment of failure. The legal ambiguity is prompting a rapid legislative response. Regional bodies, like lawmakers here at the Utah State Capitol and regulators in the European Union, are drafting strict disclosure and product safety regimes. To close the gap, they are categorizing aviation software as high risk and treating code developers precisely as hardware manufacturers. But legislation cannot solve the core technical reality. When an autonomous aircraft crashes, investigators literally cannot reconstruct the machine's exact reasoning. Despite unresolved risks, the regulatory agenda for depopulating the cockpit is already in motion. This timeline tracks the implementation of single-pilot European cruise operations by 2030. By 2032, regional cargo networks are expected to transition entirely to fully uncrewed flights. Fleet operators adopting this model face a severe financial trade-off. Eliminating human flight crews reduces direct labor costs, but it requires escalating capital expenditures to maintain secure ground control stations, redundant satellite telemetry, and constant software supply chain validation. Furthermore, until the legal liability and cybersecurity frameworks are definitively resolved, the insurance industry will levy massive premiums to cover these operations. The complete automation of flight controls is a fundamental restructuring of aerospace engineering, systemic risk, and cyber-physical security. The software dictates the economics, and the industry must prepare for the exact mathematical vulnerabilities it is installing into the airspace.